Hello and welcome to this video about proofs of theorems in linear algebra. In this theorem we'll prove that the column rank is equal to the row rank of any matrix. So we'll have to quickly learn what these things are and then we'll prove the theorem. After having proven this, we can then define a new quantity for a matrix called the rank of a matrix, which is equal to the column rank and the row rank. Because any linear transform can be written as a matrix, this theorem qualifies as a linear transformation theorem. So now to quickly learn some definitions. We can write out matrix A like this, in matrix entry dot notation. It can represent a matrix with one element. We'll let CK be the kth column vector of A. The C stands for column. Then we can write out matrix A as a collection of column vectors like this, with long straight vertical lines representing the fact that these column vectors span the whole height of the matrix. And this is what the kth column vector of A looks like if it's written in entry notation. We can write out the matrix A in column entry notation, showing each column as being a vector in matrix A. So I'll just make some more room on the screen and leave this line which we'll refer to. We can use these column vectors to represent the column space of A. This is the column space of A. It's all of the linear combinations of the column vectors of A. The column space is also the image of A if A is thought of as a linear transformation. So we can write out the image of A like this, as a set of all the linear combinations of the column vectors of A. This is really the proper way to write it. And we can write out the column space of A, which is exactly the same as the image of A. I just want to write this down, that matrices and linear transformations are interchangeable. I'll prove it in a later video, but not just now. These column vectors in A may be linearly dependent. That is, one of them can be written as a linear combination of the other vectors in the set. So we might be able to find a smaller set of vectors that can represent this same column space of A. We can find the smallest set of vectors that represent the column space of A. This set will be linearly independent, and can thus be a basis for the column space of A. We can invoke lemma 2.1 to do this. This lemma says that if a spanning set is linearly dependent, then we can keep taking vectors out of this set until we get a linearly independent set. We can find another set of vectors like this that can form the smallest set of vectors that can span the column space of A, and that are linearly independent, and that therefore form a basis for the column space of A. We'll let P be the number of these vectors in this set, and we'll let these vectors be named Z1, Z2, all the way up to ZP. P is less than N. N is the number of columns in A, and P is the number of vectors that can form a basis for the column space of A, and is always less than or equal to N. So this is how we'll describe the column space of A in terms of these new vectors. The column rank of A is the dimension of the column space of A and is equal to the number of vectors in a basis of this space, which is P. We'll just write down this definition more formally. We can similarly let RK be a row vector of A. R stands for row. We can write A like this, as a collection of row vectors stacked on each other like this, and with long horizontal lines next to them, so that the vectors look like they span the whole width of the matrix. And this is what each row vector contains in terms of the entries of A. We can also write A out like this, in terms of row vectors that contain all of these entries. So now let's prove this theorem. We'll firstly set P to be the column rank of A. And P is in this range. It can't be greater than N, because this would mean that the column space would be greater than the total number of columns in A. It can't be less than 0. We can't have column spaces with a negative dimension, although it might be interesting to find a matrix like this. But for the moment we can't have negative dimensions or even fractional dimensions in this level of linear algebra. So we'll have two cases. The first case is where P is equal to 0, so the column rank is 0. This would mean that the column space would only contain the 0 vector, because its dimension is 0. We can write this out as a set that only contains the 0 vector. So the column rank is 0. I'll just write out this equation showing that the column rank of A is the dimension of the column space of A and is equal to 0. So every column of A is the 0 vector because that's the only linear combination of the 0 vector that we can make. And we can write out the matrix A being filled with 0 column vectors. I've used long vertical lines that show that these 0 vectors span the height of this matrix. I'll just move the writing up the screen to make more room. We can now say that A is the 0 matrix, because all of the elements in it are 0, because 0 vectors only contain zeros as their entries. I'll just write out A being equal to the 0 matrix here, showing all of its entries being equal to 0. Now we can say that every row of A is the 0 vector. We can write out matrix A like this, full of 0 row vectors stacked on each other and spanning the width of the matrix, using long horizontal lines to show this. And because all of the row vectors of A are the 0 vectors, then the row space of A is only the 0 vector. We can write out the row space as being this set that contains the 0 vector as its only vector. And this means that the row rank of A is 0. And we can write out what the row rank of A is in a more formal notation. I'll just make more room on the screen by scrolling it up about halfway. So the row and column spaces are equal to each other and to the set that only contains the 0 set. I'll just write this out more formally in math language. And because their row spaces are equal, then their row ranks must be equal and equal to 0. I'll just write it out here more formally. We didn't need to show that the row and column spaces of A were equal, only that their column and row ranks were equal. We sort of overproved it, but we did need to calculate what their column and row spaces were in order to calculate their row and column ranks. So now to prove case 2, where the dimension of the column space is greater than 0, being equal to 1 or more. We'll let this set of vectors be a basis for the column space of A. And this is what each vector in this basis looks like in terms of entries. We're going to make the Z column vectors into a matrix, so we've given each entry 2 indices. We'll also set each column of A to be equal to CK, where K varies from 1 to n. C stands for column. And this is what this column looks like in terms of the entries of A. We can write out the matrix A in terms of these column vectors like this, with vertical lines to show that these vectors occupy the columns. So every column of A can be written out as a linear combination of the column space basis vectors of A, because they're in the column space. We can write it out like this in a more mathematical way. These vectors called Z are in the basis of the column space of A. The unique constants have 2 indices, because they'll form a matrix soon. So we can condense this into sigma notation, which is concise, but you'd have to get used to using it. And these constants bjk are unique for every column vector because of a theorem that we proved earlier called Theorem 2.7. So I'll make more room again and only show the facts that we need for the next part of the proof. So matrix A may be written like this, as having column vectors that are sigma sums and that occupy the columns of this matrix. A can be calculated from the product of 2 matrices Z and B, because we've selected constants for B and Z to do this. And these are all the matrices written in matrix entry dot notation, A, B and Z. We can write out this matrix equation. I like to put a multiplication sign in here because the notations can get confusing. I'd like to definitely show that these 2 matrices are multiplied together. The dimensions may be figured out from the entry indices. In fact, the whole proof revolves around this equation. You'll see how the row and column spaces are equal by seeing it in this matrix equation. You can see this diagram here showing representations of these matrices in terms of their dimensions. You can see here that Z and B are slimmer than A, and therefore Z has less columns to make a column space than A does, and B has less rows to make a row space than A does. A will inherit the column and row spaces from these 2 matrices and will therefore have column and row spaces that are definitely less than what it would have if it had the maximum row and column spaces that it looks like it could have. So I'll just shift a lot of stuff up the top of the screen here and leave stuff here I want to refer to. So I'll define Ri to be the ith row of A. R stands for row. We can write A as a lot of row vectors stacked on each other like this. Each row vector occupies the whole width of the matrix. And this is what each row vector is in terms of the entries of A. We can also write out the row vectors in A as a lot of summations for each entry. They look like the entries of matrices B and Z multiplied together. Then we can factorize the summation symbol with the corresponding Z entry outside of the row vector like this. Now we'll set the row vector of B to be this, and these are the entries of row J in matrix B. So now we can rewrite this sum using the row vector Bj. We'll write out this sum in dot notation so that we can see clearly that any row in matrix A is a linear combination of the row vectors of B and is therefore in the row space of matrix B. So these B vectors are the row vectors of matrix B. I'll just write this sentence down in English or in any human speaking language. And we can write B as a stack of row vectors like this. And this set of B vectors spans the row space of A, because each row vector of A can be expressed in terms of row vectors of matrix B. We can see this in the sum in sigma notation here, that each row vector of A is the sum of row vectors of B from 1 to P. So I'll just move a lot of stuff up and off the screen, so as to make more room. And there are P of these vectors that span the row space of A, because there's a P on the top of the summation symbol, and also because the last vector in the set is indiced by P. So now to invoke a past lemma. It says that the row space is less than or equal to the number of vectors in this set P, because these vectors might be linearly dependent, and we haven't proven that they're linearly independent. So we can find a smaller set of vectors that can form a basis for the row space of A, because we can keep taking vectors out of the set until this set is linearly independent, but still spans the space. Now we can write down that the row rank of A is less than or equal to the column rank of A. And we can thus write this more formally like this. I'll just scroll up the screen to make more room. So we can do a similar thing with the transpose of A. The rows and columns would be swapped for the transpose of A, and their row and column spaces would be swapped too, so that the row rank of A transpose will be less than or equal to the column rank of A transpose. We can write this inequality because the row and column spaces are swapped for the transpose of a matrix. And so combining these two inequalities gives us the result that the column and row ranks of A are equal, and this can apply to any matrix. So then we can define the rank of a matrix to be equal to both the column rank and the row rank of a matrix. So I hope that you found this video to be helpful and educational, especially if you're struggling with linear algebra. Please click like and subscribe if you did. Feel free to share this video and to post some helpful and constructive thoughts in the comments. Tell your friends about it if they're struggling too, and thanks a lot for watching.